Transformers are the backbone of modern AI. Introduced for machine learning translation, they have since become fundamental in language understanding, summarization, code generation, and even image and audio tasks. Embeddings, positional encoding, self-attention, and multi-head attention. These components allow transformers to convert raw text into rich numerical representations. The original transformer combined an encoder and decoder. Self-attention is the heart of transformer. As a result, the model focuses on context, enabling a richer understanding. Today, we also have encoder-only models like BERT and decoder-only models like GPT. GPT models are trained using casual language modeling. They predict the next word based on previous context. Large language models learn from vast text data without human labels. The model learns grammar, facts, and reason. Hello everyone and welcome. My name is Aditya, founder of CreateBytes and CBX. I also co-founded Aldrich Labs, Krigat, and YugYog.ai, ventures where we build state-of-the-art AI systems used in diverse sectors. At CreateBytes and CBX, our mission is to democratize AI education and help learners like you develop practical expertise. In Aldrich Labs and Krigat, we focused on deploying AI in fitness and healthcare. And at YugYog.ai, we researched cutting-edge models to build state-of-the-art surveillance systems. This session draws on lessons we have learned building these systems, and we are going to touch the very basic essence of it, which is transformers. And with this, we are going to touch transformers and understanding of transformers. Transformers are the backbone of modern AI. Introduced for machine learning translation, they have since become fundamental in language understanding, summarization, code generation, and even image and audio tasks. The original transformer combined an encoder and decoder. Today, we also have encoder-only models like BERT and decoder-only models like GPT. Each architecture has a different objective, understanding versus generating, and this shapes how they perform in real-world tasks. Think of it like the difference between a student listening and understanding a lecture versus writing an essay. Both require attention, but the purpose drives the strategy. And this brings up to a very interesting concept, which is also a research paper, Attention is All You Need. The revolution began with the 2017 paper, Attention is All You Need, written by researchers at Google. It introduced the transformer architecture with self-attention. The original model achieved record translation score 41.8 blue score against English to French translation. After only 3.5 days of training, a big jump in efficiency happened compared to the earlier recurrent neural network models. By processing all words simultaneously and using attention, transformers removed bottlenecks and enabled parallelization. The innovation paved the way for modern models like ChatGPT and BERT. And when we are using transformers, there are some important key terminologies which we should know about. So before diving deeper, let's ground ourselves in core pieces: input embeddings, positional encoding, self-attention, and multi-head attention. These components allow transformers to convert raw text into rich numerical representations, understand the order of words, decide which word matter to each other, and capture multiple relationships simultaneously. We'll unpack each of these terms in the next slides. And we'll start with the very important concept, input embedding. Each word, subword, or token needs to be represented numerically. The embedding layer converts tokens into high-dimensional vectors. These vectors capture semantic meaning. Words like king and queen or Chennai and Tamil Nadu sit together in the same unrelated word space. Models operate on vectors rather than text, allowing simple arithmetic on meanings. The embedding size depends upon the model. BERT uses 768 dimensional vectors, while larger models like GPT-4 exceed 12,000 dimensions or even more now. You can think of embeddings as the memory form of the network. They shape themselves to represent meaning. And now we jump towards the second concept, which is positional encoding. Transformers process sequence in parallel. Unlike RNNs that read tokens one by one, to let the model know the order of words, we use positional encodings to each embedding. This encoding is a deterministic pattern, often sinusoidal wave, that assigns each position a unique vector. It helps the model understand sentence structure. For example, distinguishing between India won against Australia and Australia won against India. Without positional information, the model would treat both sentences as the same bag of words. Positional encoding ensures context, much like how the order of ingredients affect the outcome of a recipe if you are cooking something. And this brings up to a very interesting an important part of this architecture, which is self-attention mechanism. Self-attention is the heart of transformer. For each token, the model computes three vectors: query, key and value. Imagine reading the sentence Amitabh Bachchan met Narendra Modi at Delhi airport. When predicting a word, the query of met asks which other word matter most. Keys identify relevant words such as Amitabh Bachchan and Narendra Modi. The value vector holds the actual information from those tokens. Self-attention combines these pieces, assigning higher weights to important words. As a result, the model focuses on context, for example, linking airport to Delhi, enabling a richer understanding. And this self-attention leads to a concept which is multi-head attention. Self-attention is powerful, but a single attention mechanism may miss certain patterns. Multi-head attention splits the input into multiple attention heads, allowing the model to attend to different aspects simultaneously. One head might focus on nouns, another on verbs, and another on numeric values. After processing, the heads are concatenated and combined, producing a more expressive representation. Think of it like consulting specialists. One doctor focuses on the heart, another one on the kidneys. Similarly, heads specialize in different linguistic signals, making the model more accurate and context aware. Now, when we are having this high level idea of different key terminologies, it's important to now think about the model design choices which one can make and things which we can do on our own. Transformers were not limited to translation. So what has happened? They've revolutionized the applications such as text generation, sentiment analysis, image processing and more. Over time, variants like encoder-only models like BERT and decoder-only models like GPT emerged, each optimized for different tasks. The right architecture depends on your goal. Classification tasks benefit from encoder-only models. On the contrary, open-ended text generation require decoders. Just like choosing between a fixed gear bike for flat roads or a geared bike for hilly terrain, selecting the right transformer variant optimizes its performance. And that basically brings up to an important concept, and we're going to jump into the detail of encoder and decoder architecture with an example. So encoder-decoder models stack encoder layers and decoder layers connected through cross attention. They shine in sequence to sequence tasks like translation, summarization and image captioning. BERT, which is BERT, is an example of this architecture. It uses the encoder to build a detailed representation of the input and the decoder to generate output token by token. When you translate a Hindi newspaper headline into English, the encoder digests the Hindi sentence with the decoder which crafts the English translation. In your daily work, think of the encoder as the listener who comprehends the message and decoder as the speaker who communicates it into another language. Now, this encoder and decoder, the way they work, if we look into the architecture of encoder-only models like BERT are built by stacking multiple encoder blocks. Because they have no masked self-attention, these models can look at the entire input simultaneously. The outputs are used for tasks such as text-to-vector similarity and classification. Imagine using BERT to rate movie reviews and Book My Show. It reads the entire review, understands the context and output a sentiment score. The model pooler layer or a downstream classifier then makes the final prediction. This full visibility make encoder-only models excellent for understanding and embedding tasks. And if we take the BERT example in encoder, which is, again, I explained the full form, which is bidirectional encoder representations from transformers. That is BERT. And remember it because you'll use this word in a very regular basis. Bidirectional encoder representations from transformers, BERT. Pre-trains, and now to understand exactly what it is, pre-trains using two objectives. So BERT has two objectives with which it pre-trains. Masked language modeling, meaning predicting randomly masked tokens, and next sentence prediction. That means in masked language modeling, certain words are hidden and the model fills in the blanks. For instance, Delhi is the capital of dash. It teaches the model model that India is likely the answer for it. In next sentence prediction, the model learns relationship between sentences by deciding whether sentence B logically follows a sentence A or not. Once trained, BERT can perform tasks like sentence classification or semantic similarity. It has 12 encoder layers in the base version and 24 and even further in the next few versions which have come up from BERT and its overall scenario. And then the way we understood the encoder architecture, let's try to dig deep into the decoder-only architecture. So if you see from the diagram, decoder-only architecture feed the input and previously generated tokens through stacked decoder blocks. Then they predict the probability distribution for the next token. Modern large language models, let's say GPT-4 or even GPT-5 and Llama, rely on masked multi-head attention. Masking ensures the model can only attend to earlier tokens, preventing it from peeking at the future words. So masking ensures the model can only attend to earlier tokens and preventing it from peeking at future words. Scaling decoder-only models improve generalization, allowing tasks like classification or summarization through prompting. This architecture underpins chatbots and generative assistants which are used in platforms like Swiggy's support chat or even other famous engines. Now we are going to jump towards a high-level categorization and differences in these. So this comparative slide clarifies which architecture to choose. Encoder-only models are best for understanding classification and similarity. Examples include BERT or Roberta. Decoder-only models are suited for text generation and instruction following, like the GPT family. Encoder-decoder models handle translation, summarization, multi-modal tasks, with BERT and P5 being notable examples. The table also emphasizes that encoder-only models see the full input at once. Decoder-only models predict the next token with masking, and encoder-decoder use cross-attention to link input and output, and it is very important to understand. Now, GPT models are trained using casual language modeling. They predict the next word based on previous context. Unlike encoder or decoder models, GPT uses only stacked decoder blocks without cross attention. OpenAI's implementation employs, this is important to understand, OpenAI's implementation employs Con 1D layers from projecting weights, a design choice, not a convolutional network. When given a prompt like this movie was a very, and then we blank it with dash, model continues the sentence in different ways depending upon sampling randomness. In practice, this allows GPT-based systems to generate creative content which can be used for marketing copies or customer service responses and all. And then if we look at the GPT architecture overview, and this is something which one can learn and understand, a very important topic. GPT is a transformer based language model inspired by the original transformer paper. Earlier sequence models like RNNs, so this is important, that earlier sequence models like RNNs process tokens one by one, struggling with long-term dependencies. Transformers remove recurrence and use self-attention, allowing parallel computation and better scalability. GPT models are decoder only with masked multi-head attention and position-wise feed-forward layers. Scaling these models improves their ability to perform tasks like classification, summarization, and translation simply through prompting. The slides shows stacked decoder block and each containing multi-head attention, feed-forward layer, and residual connection. So this is important to understand. This slide is going to explain to you, and that the reason for this is to show you a stacked decoder block, each containing multi-head attention, feed-forward layer, and residual connections that build the block of GPT. And this brings up concept which is masked multi-head attention in GPT. In GPT, scale dot product attention computes how much each word should attend to previous token. The mask sets future positions to large negative values, so the softmax function assigns them near zero attention. The steps are generate Q, K, and V vectors through linear layers, compute attention scores via dot product, apply the mask, normalize with softmax, and compute a weighted sum of the value. With multiple heads, which can be like 16 to 32 running in parallel, the model compute diverse pattern. This mechanism ensures the model writes sentences word by word without cheating. And this basically brings up to something which is called as casual language modeling. Large language models learn from vast text data without human labels. Self-supervised learning is important. And this is casual language modeling. It trains the model to predict the next word using only previous token. The training loop is simple. The model receives text, predicts the next token, appends it to the context, and repeats. Over billions of iterations, the model learns grammar, facts, and reasoning. For example, given Sachin Tendulkar is a legendary Indian, the model learns to predict cricketer. This auto-regressive training forms the basis of most generative models which are available today. And then this brings up that what are these large multi-model? While language models handle text, large multi-modal models which are called as LMMs process multiple data types which are like text, images, audios, and videos. They provide richer understanding than text-only models. Most current systems accept images and generate text, forming visual language models which we call VLMs, and we use them a lot at CreateBytes. Tasks include, like for example, image captioning, Taj Mahal at sunrise, visual question answering, what is the meaning of this, what is this man holding, and image understanding. Examples of LMMs include GIT, Blip2, Flamingo, and there are other LLMs which have come out. These models open exciting possibilities for applications like describing satellite images, for weather forecasting, or assisting visual impaired users. Now, if we look at the architecture and the training of multi-modal models, these LLMs typically consist of an image encoder and a language model. Encoders use convolutional neural network like ResNet or Vision Transform to extract visual features. The language model can be OP, Llama 2, or Flank T5, or Llama 3, whatever. Models like Blip2 or the further versions of it insert a lightweight module that connects vision and language, making training more efficient. Training uses auto-regressive loss. The model predicts the next token given the image and the previous text. Vision transformers convert images into tokens similar to text, allowing a unified attention mechanism. In practice, this means the models can describe a picture of the Gateway of India as easily as it reads a passage. Now, we need to understand this, and this is very important at the business scale, that what is this proprietary versus open source models. Choosing a model also means choosing a license. Proprietary models are like GPT-4, GPT-5, Claude, Gemini, which are accessible via only APIs or through the platform. They often lead performance leaderboards but keep weights in a very close interface, so they are not going to open those. So open models are like Llama or Mistral, which release weights but maybe not exactly the training data. And you can run the fine-tuned models by yourself, but what you need will be compute. Open source models like Llama. So open source models provide full weight and code, making them reproducible and research friendly. A recommended strategy is prototype with proprietary APIs and shift to open or open source models when scaling for production. In CreateBytes, we use GPT and Claude, and these for purposes which are not exactly related to data privacy, or let's say there are compliances which we have to follow, then we won't use it, but we use them for a lot of purposes including embedding generation. But we are using a lot of open models and open source models for our own proprietary technology. We use open source models even to fine tune the current system, because we also have the data available and then we generate a similar data from that. Now, there are some popular open and open source models which you guys should be aware about. Same, like for example, open models are shaping the ecosystem. There are several open models which are shaping the overall ecosystem. Meta is openly releasing a lot of research and commercially usable. Meta is openly releasing a lot of research and commercially usable open models with sizes from 7 billion to 71 billion to 400 or 600 billion parameters, and an instruction-tuned Llama chat variant has also been released by them. Falcon is built by TII Abu Dhabi and released under Apache 2.0 version. It includes Falcon 7B, Falcon 40B, which are trained on refined web datasets. Mistral offers Mistral 7B, Mistral 8x7B, which outperforms larger models like given Llama 2 70B. It was not able to with Llama 3. Mistral large and small support JSON mode and function calling, etc. Dolly 2 based on Pythia 12B model, which is also available. Open Assistant is a community. I'm going to give a quick brief around this thing which is called as Open Assistant. It's a community driven project trained on more than 600,000 human interactions across languages. But I want to again emphasize this part, and I'll try to describe that again. Several open models are shaping the ecosystem, right? Meta is openly releasing research and commercially available models which can vary from sizes like 7 billion to 71 billion parameter. An instruction-tuned Llama chat variant has also been released by them. Falcon is built by TII Abu Dhabi and released under Apache 2.0. These versions include Falcon 7B, Falcon 40B trained on refined web dataset. Mistral offers Mistral 7B and Mistral 8x7B, which outperforms some of the larger models like even Llama 270 billion parameter. Mistral large and Mistral small support JSON model and function calling activities. Dolly 2.0 is based on Pythia 12B and trained on Dolly 15K instruction dataset, which is fully open source. And finally, Open Assistant is a community-driven project trained on more than 600,000 human interactions across languages. These models provide flexible starting point for organizations, startups who want in a transparent mechanism take control of the models and use it for a lot of business purposes. So it's important that we keep on exploring. If you want to know more about it, join our Discord community and we can give you a lot more details around some of those open source projects. So with this, we come to a conclusion, and I definitely want to give a quick brief about CBX. So at CBX, we believe learning is a collective journey. By joining our community, you gain access to AI workshops and masterclasses led by top experts. We provide curated resources to help you stay ahead of the curve, along with exclusive AI mixers in Delhi and other places, and we do regular hackathons. It's a place to connect with fellow AI enthusiasts and build projects together in an open source environment. When you scan this QR code on this slide, you'll get across to our Discord community, and you'll get links to follow us on Insta and YouTube, where we share a lot of different snippets of what's going on in AI and then some industry news, plus a lot of interesting tools which are available there. I hope this discussion has demystified transformers and shown you how you can apply them to solve meaningful problems. Let's continue to learn and build together. Thank you.